Okay, welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Dr. Xian Zhuo-Yu from University Würzburg in Germany. And our scientific host today is Dario. And Dario, please ask you to introduce our speaker.
Yeah, thanks, Tilen. It's a great pleasure to have Zhuo-Yu today from Würzburg, let's say virtually. So let me introduce the speaker. He got his PhD in theoretical physics at the Chinese Academy of Science in Beijing in 2018. Then he spent a couple of years more as a postdoc still in the Chinese Academy of Science. And starting from 2021, he finally moved to Germany, where he's working as a postdoc in the group of Professor Johanna Ermenger and René Meyer. Now, introducing the research interest of our speaker, as we can read here, so I just have to read. They are, let's say, at the boundary between gravity and condensed matter, because he can talk about ADS-CFT, which is, let's say, an MTH topic, the S-Waker model, which is both, but also quantum chaos and quantum information. So we could say that overall, his research topic is, let's say, quantum many-body systems. And one of the topics where he is working is the notion of complexity, and in particular K-complexity, which is a topic that we are also, let's say, studying here, some of us, at least in PCS. And today's talk will be exactly about this. So it will be about chaos and Krylov complexity. And I ask our speaker to start the talk. Yeah, thank you.
Yeah, thanks for the detailed introduction. Yeah, nice to see you, everyone here. I will give some talk about the chaos and chaos complexity. Yeah, but I must say during this talk I will not mention much thing about ADS-CFT and either SYK, but really focus on chaos and some calculation in the chaos complexity and some observation between the relation of chaos and complexity. Yeah, the outline is simple. I will talk about some chaos first and mainly focus and then connect it to the spectrum statistic and see and then consider some chaos complexity and show how does it relate to the spectrum and then study the evolution of chaos complexity in two time scale. One is early time and the late time, and finally come to our conclusion. So we better start from the classical chaos. I mean, in the classical Hamiltonian mechanics, there's two radical different type of motion. One is a regular motion in the integral system for some like this rectangle billiard. All the trajectory is go in a circle, but something different if we consider such so-called sinus billiard, where people put a circle infinity potential inside the square potential, and if we start from two close trajectory, if we consider the two trajectory which originate from two close point in the phase space, like this case. So their distance will grow exponentially like this, with a exponent lambda L here. They call them linear exponent. So actually this phenomenon is very it's very universal, no matter except for some special point. Most of the point in the phase space in this model will follow the similar instability. I mean, if you consider a very small fluctuation or very small deviation from the beginning, then the distance will grow exponentially. So this will be called the chaos motion of in an non-integrable system. So now in the classical motion, we have such a very radical different type of motion of classification. However, can we consider some quantum version of this model? For example, if we consider some wave function with some mass and living propagating in this rectangle period, in this rectangle potential or this shape of potential, can we see something? Can you see something dramatically different between these two models? Okay, and now it comes to the problem we are interested in, the quantum chaos. But here is a conjecture based on the spectrum of the wave function of the Schrödinger equation propagating in these two different potential. But here is so-called BGS conjecture. Namely, if we solve the eigenvalue of the Schrödinger equation in this shape of potential, we will find and study the statistic of the energy level. So in this original paper, they observe some very universal behavior. For example, here in this figure, they show the so-called they study the level spacing, where x is the difference between nearest neighbor energy. So they find that the probability of the distribution of the level spacing behave like this histogram curve. Actually, this paper observed that this probability satisfies the Wigner-Summer rule given by the random metric theory. For example, in such a linear builder, it obeys the Gaussian orthogonal ensemble case behavior like this. Furthermore, the author also observes another property related to the chaos, the so-called spectral rigidity, namely the number of levels within an interval of given length has small fluctuation. For example, if we have a sequence of energy and we choose a window, the length of window is L here, but of course we can move the location of this window and study how many levels inside these windows. So actually, they found that the number has a very small fluctuation, and quantitatively we can study the so-called we can count how many for a given energy epsilon here, we can count how many levels are between the button of the spectrum and the energy epsilon here. We call it n, and then use this quantity to study how close the n as a function of epsilon, for some as a linear function of epsilon. So they find that the data 3 here, by averaging the location of this fixed length interval, behave like some logarithmic function as a function of the length L here. So it's much different from a random level, a random and uncorrelated level putting on the interval. In that case, the data 3 here we follow the Poisson distribution, like a strange curve. So these two typical behavior was found to be very universal in most of the quantum system with classical description. And so motivated by this, we can, as I say, yeah.
Just the question is that, so ME epsilon is not the density of state, right? It's the, is the number of,
yeah, so epsilon is the energy. Yeah, it's energy. I mean, so consider
of epsilon?
Integrated spectral density.
so can you? I think epsilon, but n is a number. N is a number between the button and n is a number in the interval between the button and the energy epsilon. Just counting how many spectrum below this energy.
Right. So
and
if I choose A is equal to B is equal to 0, then delta 3 will give me the density of state.
No. Wait. This delta 3 is not the density of state. We are just here. This quantity just estimate how close does this n epsilon behave as a function, as a linear function of epsilon. How close does it behave like a linear function? I mean, for example, if I consider a very homogeneous spectrum, I mean, all the level spacing are the same. So of course here n epsilon is a linear function. N here is a linear function of epsilon. So now the delta is equal to 0. Delta 3 is equal to 0. But of course, there's some fluctuation in the spectrum. Of course, in the usual system. So that fluctuation will lead to the deviation from the linear behavior. So then we got a non-zero delta 3, but this delta 3 is not in the chaos spectrum. This delta 3 is not. It just behaves like logarithmic function as L instead of the linear function of L. In contrast, in the integrable system. For example, if you study the spectrum in this rectangular, which is the integrable system, then you will find delta 3 will obey the Poisson distribution as a linear function of L. Is it clear?
Yes.
Yes. Yeah. The answer question. Yeah. Okay. Yeah. Because both this property is related to the spectrum only. So there's another quantity which relate to the time evolution, but can encode some property, these two property during the evolution. So one can given Hamiltonian, of course that for example the Hamiltonian in this sinus beta, and one can once we extract its spectrum EP here, and we can construct the so-called spectrum form factor like this. Here I also consider a finite temperature, but of course for simplicity we can send beta to 0 and only consider the time evolution. And here actually from this expression, the so-called spectrum form factor is nothing but the Fourier transformation from the energy difference to the time. But however, here I try to write in another way. The spectral form factor is also given by the survival probability of maximally entangled state. Here, psi 0 is a maximally entangled state in the double copy of Hilbert space. Originally, we have a Hilbert space, and then I make a double copy of it, and combine two of them and call it H left right, and left stand for this Hilbert space, and right stand for this Hilbert space. So now if I construct a maximum entangled state in this state, and then calculate and then consider the evolution of this state by this Hamiltonian H. So this H is the Hamiltonian in a single Hilbert space, and out of that with identity. So sometimes we call it Euclidean. You will see similar evolution operator in the Krylov case. So now, if we consider evolution of this maximal entangled state and consider the overlap, the so-called survival, okay, the overlap with its initial state, and then consider probability. So it's easy to see that you will end up with this spectral form factor summation. Okay. And let's talk about the time evolution of the spectral form factor. There's two, so correspond to these two characteristics of chaos in the spectrum. There's some correspondent behavior in the spectral form factor. First is a very late deep time. Yeah. Oh yeah. We better have a look at the typical behavior of the spectral form factor in a chaos system. First, when t equals 0, of course, the overlap is 1. Okay, with some normalization. And however, during the evolution, this state will deviate from the initial state, so the overlap will decrease. And we call this decrease as slope. And then, however, until some time, here is the so-called deep time. Is ordered by a square root of L. L is the size of the dimension of Hilbert state. And then it will, after this deep time, it will increase with a linear behavior. We call this regime linear ramp. This linear ramp is exponential. It's very long. So this ramp will stop until until the so-called plateau time. The plateau time is in the order of dimension of Hilbert space. So relatively, this ramp is very long and linear. And then the spectral form factor will go into a plateau regime. Okay. Basically, the slope, ramp, and plateau behavior is the typical behavior of the spectral form factor in a chaos system. So actually, the ramp here, this linear ramp is a property of the correlation of the density of energy. Now the rho here is the density of energy, and the delta rho here is considered the delta rho here is the derivation from the derivation from the semi-circle law, its expectational value. So here you can see the correlation of the density in different energy. So we consider two different energy, E1 and E2, and consider some fluctuation of the density in this energy. So you can see the correlation is decreasing if the energy become longer and longer. If the energy become far from each other. So actually, here is nothing but the spectral rigidity, because for some consider an interval, and the energy in the energy on the two edge of this interval has a very small correlation if the interval become larger and larger. So then you will see why does the theta 3 here will decrease compared to a linear behavior. So here I just want to say this decreasing correlation between the energy density is related to the spectral rigidity in the and then with this correlation we can calculate the spectral form factor based on this correlation, and we will find a linear ramp in this regime. So here I just want to say the linear ramp here is it starts to this correlation of density, which characterize the property of spectral rigidity, and so the presence of long ramp, linear ramp here corresponds to the chaos. So here's the take-home message I want to show here. Is there any question? Oh,
Sorry.
okay.
Yeah, we are.
So in the definition, you have a beta. For
Yeah.
But in the plot, you don't.
Yeah, I said, as I say, for simplicity, I set beta to 0. Yeah, but generally we can consider beta.
If I include the beta, will the oscillation in the initial part die down, or what will happen?
Yes.
Usually this oscillation will become small. Yeah.
Okay.
Yeah, but the typical behavior, slope, ramp, and plateau behavior will not change.
Okay. Thanks.
Okay. And also their scale with the size of Hilbert space. Yeah. Yeah. So of course, for plotting this figure, I consider some typical model. So as I say, here is the as I say, the chaos spectrum could be rarely described by some random metric theory. Here I take a very special random metric theory, the so-called Gaussian unitary ensemble, and calculate the special form factor numerically. Of course, to show this behavior, I actually also consider a huge ensemble for some thousands of realization, and take the ensemble average and got this plot. Yeah. Otherwise, there's some you can see there's a very huge oscillation in the ramp region and also plateau region. Yeah. Here I just want to show the typical behavior. So it looks very smooth, but actually it fluctuates very quickly. Yeah. I will if I have time, I can show why does happen. And then after this after our analysis on the spectral form factor, I try to relate it to the Krylov complexity. Of course, not all the complexity is described by the spectral only, but only this spectral Krylov complexity is only determined by the spectral. Here I follow the I take that maximal entangled state, MES maximal entangled state precise here, and evolve it by some by some imaginary by some complex time. So this evolution can encode Euclidean time evolution and also Lorentz time evolution together. So because the beta, the inverse temperature here, usually people call the resulting state as the Sommerfeld double state. Okay, because the evolution here, the Euclidean time evolution here will suppress the high energy spectrum. So something looks like so this behavior looks like some finite temperature, some we suppress entanglement, so and behave some finite temperature state if we trace out one of the system. So people call it Sommerfeld double state. So let's follow this notation. So precise tau here is we call it TFD state for short. So of course, if we consider all the tau from 0 to infinity, okay, it will spread over some subspace in the total Hilbert space. So the so-called Krylov space is justified by the largest space where the psi tau explored. So for example, like this figure, remember that the maximal entangled state is a state in the double copy Hilbert space. So also the psi tau is also living in the double copy Hilbert space. And however, under the time evolution, this state will propagate for some along some very some trajectory and become and end up with some the Sommerfeld double state we study. And if I consider all the temperature all the time here, it can explore some sub-regime in the double Hilbert space called kappa here. And of course if a matter of fact, if H Hamiltonian here have no degeneracy, it's easy to check that the dimension of the Krylov space is L. Also, in other words, the dimension of the Krylov space is the same as the dimension of the single Hilbert space. So,
sorry, this is true for any state, or is true only for the maximal? Only if you start from the maximally entangled state?
Only for the maximum entangled state, of course. Yeah. For example,
Okay.
if you consider, so I will show you in next slide. If you consider some deformation, for example, you insert an operator on the precise tau, then you will change the dimension.
I see. Okay.
So, but yeah, actually, this problem is very simple because you can if you have looked the expansion of the semi-filter say in the energy basis in the double Hilbert space, you can see the energy is always diagonal because this state is only evolved by this Lewisian, which is construct from the Hamiltonian only. So yeah, this reason the dimension is very small compared to the total Hilbert space. And now one can define the so-called Krylov complexity in such a way. Now we can define a Krylov complexity as an expectation value of some operator. We call it complexity operator and sandwiched by the semi-filter say. And how can we construct this K hat? Okay, from the Krylov construction, we start from the maximal entangled state and keep applying the Lewisian or Hamiltonian on top of this maximal entangled state and generate a sequence labeled by n here by the power of L. And of course, as I say, this up to the finite dimension of the Krylov space here, this sequence will not generate new state when n is greater than L. So actually, if we do the Gaussian-Smith orthogonalization on this sequence, we will get some orthogonal space. Let's call it ON. O stands for orthogonal. This state also. Not surprised, this state, the basic only has L state, and based on that sequence, we can define the so-called complexity operator with an eigen, which is diagonal on this Krylov basis. Okay, yeah, we call this O as Krylov basis. So in this figure, I'm showing some. Also some typical behavior of this Krylov state complexity. Oh, awesome.
We have a
Question. So the maximally entangled state, can I understand this as the density matrix, the identity density matrix in the vectorized notation?
The identity density matrix in what? Sorry, the last I can't hear the last.
So if you go back to your, if you go back to the definition of your spectral form factor.
Yeah, okay.
There you start with the eigenstates of the Hamiltonian, right?
Yeah.
So then I can write down a density matrix for that Hamiltonian, and the maximally entangled state will be when the density matrix has all identities.
Yeah, exactly.
And so then are you just considering the vectorized notation of that? Like you vectorize that density matrix and then that gives you that maximally entangled state. Is that the statement? Or how do I understand this, like two copies of left and right, and then you are doing the evolution with just an operator, with just an Hamiltonian defined on the left. So I'm just trying to get a physical picture of, because originally you just have the left, so as to say.
Yeah, exactly. Yeah, exactly. Okay. Correct. So it's very simple. Okay. Actually, yeah, you're right. But the so-called density metric you're talking about is the reduced density metric of this maximal entangled state. If I trace out one part of the, for example, the right-hand side Hamiltonian, the right-hand side Hilbert space. Yeah, exactly. Then I will end up with some identity, just identity operator. Okay, in this single Hilbert space. Exactly. Here I just play the same game. I just you can say I just play a trick by consider a double copy of the Hilbert space and map an operator in the single Hilbert space into a state of the double copy Hilbert space. Is it clear? Yeah.
Maybe I can add a comment. Yeah.
I just want to understand the definition, because here you have a particular Hamiltonian on the left, and on the right you speak about ensemble. So what is in the plot? Is it ensemble average, or it is particular realization of random matrix? What is plotted here? Is it ensemble average, Z?
Oh, yeah, exactly. I said, exactly. In this plot, I should write the ensemble average of C. I mean, I consider a lot of realization of the Hamiltonian from the so-called Gaussian unitary ensemble, for example, thousands of them, and then for each of the Hamiltonian, I calculate the Z here, and then I take an average of all those thousands of Z and show and plot the average value. So actually, in this figure, of course, I wonder, as I say, I'm showing the average, the value of the Z. If you only choose one realization, this Z will not look like so simple here. It will have very strong fluctuation. It's not. Is it clear to you? I mean, in this figure, I'm plotting the average value of special form vector in for example thousands of realization in one ensemble. I have thousands of Hamiltonian, and I just show their average result.
Maybe I can also add a comment to what you can think about the thermofield double state as the purification of the maximally mixed state living on one of the two systems. You know, the usual thing is that when you have a mixed state, which is not a cat, can be described as a pure state in a purification space, which is double the space. So what is doing here is exactly the purification of the maximally mixed state in the left system.
So what I was confused is that if I just start with the density matrix, I can
density matrix living where?
Density matrix living on the left space.
Correct.
And then if I just write down the vector corresponding to that, I can vectorize that. So is it related to that or no?
Probably yes, but yeah, the precise definition is that you want to purify the mixed state, the maximally mixed state living on the left system. And to do that, you have to do this procedure and you end up with that. Or turning things around, you can check that if you start from that state, you construct the corresponding density matrix and you trace out the right system, you get the maximally mixed state on the left.
Thanks for the comment. Oh, so is it clear now?
I think so. Yeah.
Okay, thanks. Yeah. So come back to the story of Krylov space. So here I'm showing the typical behavior of Krylov complexity. Of course, here I also take the average ensemble. I mean, in principle, I should put a bracket here, but yeah.
And again, sorry. What you are plotting here is the ensemble average, fine, but of the what is the name? I lost. Yeah, of the Krylov complexity. When you start from the maximum, I mean, if you change the initial state, you have very different behaviors of this K of T, right?
Yeah, of course. If I change if I use a small operator to deform this state, usually the behavior will change.
Okay, good.
Yeah.
And here you are taking, sorry, then I let you go. Here you are taking the case, in which the Hamiltonian is just the G. It's just the GUE. Okay, so it's
Okay. Very simple.
Okay.
So here's the typical behavior. First, you undergo.
Krylov complexity is also ensemble average, right?
correct.
In this plot, I'm plotting the ensemble average similar to special form vector. But for this single realization, one can calculate one can even calculate Krylov complexity for each realization. Okay? But for plotting the plot, for plotting this figure, we do better plot some average value for the.
So it's indeed different for different realizations. Yes.
Yes.
Yeah, of course.
And,
in different realization, the K will behave slightly different. But however, the Krylov complexity has some advantage that we call it self-averaging. So because it means usually you take any. I mean, if you only take one realization from the Zhuo-Yu and calculate the Krylov complexity following this process, you will find the curve is very stable. I mean, the fluctuation is relatively small compared to the spectral form pattern. Okay.
But what I want to tell you is that if it is so, then this K before averaging should be invariant under unitary transformations, because if you take random matrix and make arbitrary unitary transformation, you get another member of the ensemble. And that's why it's worthwhile just to check if under unitary transformation this definition remains invariant.
Yeah, invariant. Yeah, invariant. Yeah. Actually, when you mentioned
transformation, so there is huge symmetry group.
Yeah, you're right. Indeed, if I consider a unitary transformation on the Hamiltonian, indeed, thanks for pointing out this property. Yeah, actually here, the maximal entangled state is not unique. Actually, I can apply unitary transformation on each basis. If I change the basis, the calculation, I mean the spectral form pattern and also the Krylov complexity will not change the value. If I apply unitary transformation on each single Hilbert space, and they will not change. It means I change the basis for the maximal entangled state, but you will end up with the same spectral form pattern and the Krylov complexity. Yeah. So is it clear?
More or less.
Okay, thanks. Yeah. And then so this figure shows the behavior. So first it has an goal of projected growth and then linear growth, and reach a peak, and then saturate and decrease and saturate. Okay, here's a typical behavior. I will in the later part of this talk, I will show which behavior. I mean, for example, which behavior, the linear or peak or even saturation, which part of this behavior is related to the property here, spectral rigidity. And just as following similar story in the spectral form method. Okay. Of course, because Darius also mentioned the operator complexity. Here, you can see the title here. I'm talking about state complexity. Of course, we can generalize this construction to the operator complexity by use the so-called GNS reconstruction. So assume we have an operator where, for example, very small operator over here, and then we can define the Krylov KC stands for Krylov complexity. Krylov complexity of this operator as the Krylov complexity of this state. And how can we construct this state? Given that maximal entangled state, and then I construct this this operator. I mean, I put the operator we are interested in on the left-hand side and output that with the identity. And we apply this operator on this maximal entangled state, and we end up with some operator deformed entangled state. Yeah. But now we can. However, here we should slightly change the Liouvillean. Is like this is the identity times Hamiltonian and minus the Hamiltonian times identity. Out of that. Actually, it's easy to see that if you apply the L on this operator deformed maximal entangled state, you will end up with some commutator of the O inside this bracket, because here you can see H times on the right hand side, this H times on the right hand side of the O, and this H times the left hand times the O from left hand side. So and there's a minus I give the commutator. So this spring, so one can simply use this framework to study the kilocompressive of an operator. Similarly, in this paper, they propose a hypothesis for the chaos for the complexity of operator in the chaos system. They observe the so-called the exponential growth in the kilocomplexity before time scale. They call it scrambling time. However, this time scale is much earlier than this 2 time scale. Okay, I should stay in there. All right. And this exponential growth time scale with a exponent 2 alpha here, and the author in this paper shows that there's an upper bound. This 2 alpha exponent here is an upper bound for the Leonov exponent given by the out of time order correlator defined in this way. Yeah, here's about here's the story here is quite long. People find that in the general system, especially the chaotic system, if we study the commutator square in that system and consider time evolution, it will grow exponentially, just like something really just like what we observe in the classical chaos case. And this exponential, this reason why they call this lambda L as a Leonov exponent, even in such quantum system. So, however, in this paper, found that there's the 2 alpha here in the divided by the kilocomplexity of operator is bound this Leonov exponent from above. Okay. Of course, they check a lot of system in SYK model, some chaos or spin chain model, and they find this bound always true. And also this exponential growth, this exponential growth seems to be very universal in a chaos system. But if they consider free system or even integrable system, they found there's no very obvious exponential growth for the kilocomplexity. And in this figure, I'm showing the BN. Of course, BN is different from the kilocomplexity. It's we call it Lanczos coefficient. I will show you later. Here the take message is just the linear growth of Lanczos coefficient corresponds to the exponential growth of kilocomplexity. Okay. However, okay. Later on, okay, there's some following up paper find that this exponential growth of kilocomplexity was also found in even general two-dimensional CFT, and even some free field theory, and also some integrable system. They found some example like that. So I must say, unfortunately, I mean, this exponential growth of kilocomplexity may not be a good characterization of chaos of quantum chaos if you consider very general system. Okay. However, okay, people also found some relation between this kilocomplexity and some complexity defined in the ADS-CFT side. Okay, we call it a volume complexity. This volume is just given by the Einstein-Rosen bridge in the eternal black hole. Actually, but however, the story is too long. I just want to give some short message. I mean, if the operator just like some deformation, you flow into a black hole. Some matter you flow into a black hole, and this deformation will make the black hole grow slightly. Okay, and then this small deformation will grow during the time evolution of black hole inside. If you consider if you choose the evolution of black hole in the proper way, then you will see the volume inside this black hole. We call it Einstein-Rosen bridge. Okay, has an exponential growth. So also I have a rule following this idea and compare the growth of Krylov complexity and the growth of volume in the black hole. They see where we see similar exponential growth behavior in both cases. So is there any question? Okay. So compared to the yeah, here we explain some Krylov complexity. In principle, I should review some Krylov complexity, some complexity if defined in other system, but down to the time limitation, I will just skip this part. I mean, I want to say there's another definition of complexity, but however, compared to them, Krylov complexity has its own advantage. For example, in this case, the Krylov complexity do not take care about the locality, and also the definition of hard or simple operator in the operator set. Also, at early time, it may characterize probably characterize some early time chaos around the scrambling time scale. However, actually, we will show that at a late time, it also characterizes chaos, but that chaos corresponds to has different origin. That chaos is exactly related to the spectrum property I show in this figure. So here's the question I want to ask. So what's the characterization of chaos in Krylov complexity, and how does the Krylov complexity relate to spectral form factor? And now it come to our paper recently, but I will not show much detail about that. I just want to tell some take-home message. Okay. So to calculate the Krylov complexity, we should build a Krylov basis first. So also based on this orthogonalization, assume that we can calculate the orthogonal basis here, and then the Liouvillean is tridiagonal in this basis. Looks like this with A and B sequence. We call them length source coefficient. There's a typical behavior from the Gaussian unit example. In the length source coefficient in average behave like this. I mean, for A is average A is vanished in average, and B ends behave like 1 minus n divided by L. In this way, here is some realization, some length source coefficient for one realization of GOE. Okay. With this observation, now if we consider the sum-infinitable state and calculate the evolution of this sum-infinitable state as a function of tau. Okay. Now we can define an ON, which is just the overlap between the sum-infinitable state and the Krylov basis. The ON just behave like some wave function, but living in the one-dimensional chain. We call it Krylov chain. And here's the discretized version of the Schrödinger equation describing this this phi n coefficient. And then once we study the evolution of this ON, then we will calculate the complexity by consider the quantum average. Here's a typical behavior of the Krylov complexity of this ON. Okay, so you can see at small time, when time equals 0, it's a delta function here because the only overlap because it only overlaps with the ON, the original operator, the original state, and then it will try to propagate along the Krylov chain in this way, and finally it will reach the upper edge of the chain and start to diffuse. Okay, so actually we find a generalization from this so-called iron flash theorem from this paper, in the which describe the evolution of Krylov complexity in the second derivative of Krylov complexity in this chain. And we find that if we plot the behavior of Lanczos coefficient in the Gaussian unitary ensemble, and then we can simplify this expression here and end up with something like this. Z is exactly the special form factor we see before. So in this formula, you see this formula relates the growth of Krylov complexity to the spectral form factor. And furthermore, there's a more interesting correspondence. If we see, here's a double derivative. If we take the double integral along time, we will end up with the Krylov complexity, and we find that it's exactly the same as the so-called spectron complexity, defined this way. We label it by C, and this spectral complexity is derived from the two-dimensional gravity in the relative gravity in this paper. So it's very interesting correspondence in once we observe the average behavior of the Lanczos coefficient in the random measure model, and then let's calculate this spectral complexity. To calculate this, we need the 1-point and 2-point function of spectral density in the GOE, and just be like this. We here is a so-called sine kernel. When we calculate this, the spectral complexity has a quadratic, linear, and saturation behavior in different time scale, shown in this figure. So as you see here, this time scale this behavior is already similar to this numerical result we find in Krylov complexity, but at the later time it has a very small deviation. The dot here is the spectrum, that is the Krylov complexity. The solid line is the spectrum complexity. I mean, the linear growth of spectrum complexity is well described. It can well describe the Krylov complexity. But after the peak, this peak in a Krylov complexity, they start to deviate from each other. Here I just call I just call this linear growth as the early time of the Krylov complexity. But after the peak, I call it the late time. So for the as a matter of fact, this linear growth of the Krylov complexity and also the spectral complexity is only given by the slope instead of the ramp of the spectrum of the spectral form factor. In other words, there's a take message. In this case, the Krylov complexity of a maximal entangled state may have a linear growth, but their linear growth is not related to the quantum chaos. I mean, because it's not given by the ramp, it's only given by the slope. So basically, it's only given by the 1-point function of the density, the energy density.
Sorry, but can you relate this linear growth to the behavior of the OTOC?
No, not yet. Usually, if you calculate the OTOC after the exponential growth, then Krylov complexity will go across to the linear growth regime. But that linear growth, but that linear growth may relate to chaos in another way. But at least, however, in this case, only for this special maximal entangled state, the linear growth is not related to chaos. Yeah, this I cannot eliminate. I cannot exclude the relation between chaos and in the operator complexity case. Okay. I mean, I cannot exclude the relation between chaos and chaos operator complexity. But here I just talking about the state complexity and I find that the linear growth is not related to chaos.
So wait, this linear growth must be related to the integrated density, right? And not to the check. You are computing something like a density correlator, not a density correlator. Am I right?
Yeah, exactly. But
indeed.
Yeah, exactly.
No. Yeah, indeed. You are computing the one essentially.
Yeah.
Okay.
Yeah, he is correct. But let me tell you a fact. If I just delete this term, then I will still have a linear growth.
Exactly.
Yeah.
Exactly. So what you are seeing is something related to the density correlator and not the density. Okay.
Yeah, exactly. Yeah.
Got it.
Yeah. But and then in the following slide, I mean about the late time, then I will show you that the peak here is related to the this sine kernel. But about the calculation is slightly long. But I mean I just want to tell you the reason, the simple reason. Okay, here is in this plot I show the transition probability. The transition probability is nothing but the phi square. Okay, the phi square. Of course, it looks slightly complicated, but for example, we can have look this curve, orange curve, and then you can see it has a this curve is for n equal to 31, like this, and you can see linear rise. There's a rise and slope and ramp and then plateau. So and actually, we found this behavior is very universal, even you consider other n, but however, here's linear plot. So here log plot. If you see if you look the transition probability in the linear plot, you will find that this orange curve is here. Okay, you can see indeed there's a ramp, but for the large n, I mean this small n. Okay, for large n, for example, when n is even close to the size of Hilbert space, and it has a different behavior. It grows and it grows and there's a slope, but the ramp is not ramping up; it's ramped down. Okay, and also the saturation is it's much later than the plateau time. Here's our numerical observation. Of course, we try to construct. We try to reproduce this behavior for when n is small, when n is at least half of the. Lesser than half of the chain. Okay, but in our paper, we are unable to construct, we produce this ramp down behavior, because in this case, it's not only described by the two-point function, because in the Krylov complexity, there is a so-called orthogonalization process. That orthogonalization is a very correspond to a very high point function in the ensemble area, in the random matrix. So not only two-point function is involved at the late time of Krylov complexity. But however, there's a very simple method.
Wait, this one also is strange, because you say the ramp in the spectrum form factor can be computed out only of the two-point function. You don't need anything else, right?
Yeah, exactly. Yeah.
Here you are saying that you are computing something that depends on much more than the two-point function. So it's a little bit strange, right? It looks that you are describing something like more the level repulsion. The level repulsion depends on all the.
Yeah, exactly. Yeah. I mean this. Okay, this observation is like this. Okay, because for example, one can work out the moment. If you remember, in the Krylov complexity, we can define the to do the orthogonalization and work out the Lanczos coefficient. There's another method. We call it moment method. When you calculate the moment, you can calculate a lot of the moment and then calculate and then construct the based on the moment, you can construct the Hanker determinant of the moment, and then you construct the length of coefficient. In that Hanker determinant, there's a lot of moment, a multi-trace inside that determinant. So actually, it's related to the higher point function. Okay. For example, I will show why do I observe I will show why do I think it in this way. But in the next slide, okay. Here I just want to show some very simple method to calculate this peak. Here we can use the continuous limit in the Krylov complexity and work out the continuous version of the Krylov basis and just construct the complexity operator here, which is only a function of the energy difference, okay, S. And once we integrate over the energy difference, we end up with some peak. Exactly like what we see in the numerical result, and then go across to the plateau. However, this slow decay is the slow decay have not been observed. The slow decay we observe in numerical calculation cannot be reconstructed in this limit. The reason is like this. Okay. Now I come to a question. Okay. Also, if you but before that, let's show the long-term average of the Krylov complexity. Actually, here this bracket infinity means that I integrate over all the time and then consider average, a long-term average, and then and this long-term average can give our value for the plateau and the saturation of the transition probability and also the Krylov complexity. And here you can see the transition probability is 1 over L, and with if we study the fluctuation together, you can see the fluctuation is even in the same scale as the transition probability, just similar to the special operator. It means that this behavior explains what we observe numerically for one realization of transition probability. You will see a very strong oscillation. Yeah, it's up to this fluctuation. However, in Krylov complexity, it's different. His L minus, yeah, so here's the Krylov complexity is only will saturate to the value of as a half of the dimension of Hilbert space. Actually, this behavior is very universal. In this derivation, I only assume there's no degeneracy, and I never assume that the spectrum is chaotic or not. It means in this case, in this special case, okay, the saturation value for the Krylov complexity has nothing to do with chaos. But however, the fluctuation of Krylov complexity is different. You can see it's a square root of L. So compared to the saturation value of Krylov complexity, the fluctuation is a little bit small when L is large. Okay, and this behavior relies on the chaotic spectrum we consider. So yes, so this inequality also explains the fact that when you calculate the Krylov complexity in one realization of Hamiltonian, you will not see very strong fluctuation. Yeah, because when the size of Hilbert space is large enough. So here's the saturation value. And how about the ramp? Actually, the ramp is given like this. Okay. Now we come to the point you ask. Okay. Here's the transition probability. Psi is some polynomial. Actually, psi is a polynomial when you do the orthogonalization on this model. When you consider orthogonalization, I mean this. So in principle, this orthogonalization process relies on the inner product of the in the Krylov space, which also relies on the concrete spectrum you consider in the Hamiltonian. So actually in this polynomial also relies, there's underlying dependence on the spectrum itself. So when you calculate the transition probability in this way, for example, in this way, we can first calculate the spectrum form factor, but with some different time. Okay, T1, T2. T1, T2 is and T1, T2 is here because we want to think this spectral form factor as a generator of the transition probability, and then we take the derivative for the T1 and T2. And the derivative is inside the polynomial, and you find that if the derivative is not very, sorry, if the degree of the polynomial is finite, you will see the linear growth. Which this behavior explains what we observe here, the linear growth we observe in the transition probability, but maybe with a different coefficient. Now we come to the point. Okay, actually the psi is given, the polynomial in kilo complexity is given by the orthogonal process. So of course, if it depends on this argument, the energy, it also depends on all the spectrum. So when you take the when you take the ensemble average on top of all of them, so this rho, this E energy here, spectrum here, will correlate to the energy here also, the energy in the one-point function also. So there's a reason why I say the only two-point function may not be enough here to calculate the full Krylov complexity. Is it clear for you? Because
I think so, but I mean, it looks that this Krylov complexity is computing a bit too much in the sense that, I mean, it would be better probably if you can cook out a quantity similar to Krylov complexity that just depend on the density correlator rather than.
I hope so. Yeah, indeed, you're right. The spectral complexity here, that's what's defined in this paper, indeed only relies on the two-one function. You're right. So in this case, so this is the reason why at late time they're different. Okay, so for the spectral complexity, after the linear growth, it just saturates, and this saturation value depends on the sign kernel.
I see.
Yeah. However, in this case, the late time of Krylov complexity, as I show here, it's just L divided by 2, which is not related to any density of energy. Yeah, says this reason. Okay, I say okay. There's a quadratic difference between the different complexity at late time. So yeah. So and now after time limitation, I will quickly explain why does the peak, I mean the peak here or the peak here, is related to the chaos. Okay, this is a very simple observation. Okay, here okay, based on this sorry, can you
no, it's a noise which is coming from outside. Yeah, let's focus on this slide. Sorry, and if you remember the behavior of this transition probability, it behaves like a wave propagating from the left-hand side of the train to the right-hand side, and then here you can work out the characteristic curve in the of this propagation in the continuous limit. I mean, at time t, the peak of the wave, the transition probability is located here. Okay, so now if we assume there's a ramp in the transition probability for the m smaller than the peak, for something like this. Okay, and then we apply the probability conservation here, and then we can work out the upper bound of the peak of that transition probability on the end, okay, on the side end, and then we can work out the upper bound for the Krylov complexity, which and by the standard formula, and then we will end up in this formula, and you can see in this formula it has a peak around t equal to around half of L, which this time scale is the same
half of L. It's the same in what we observe in the numerical calculation. So here, this argument shows the role of the RAM. Okay, because there's a RAM in the transition probability, which is suppressed by the L square, then the peak in the transition probability on the largest on the side end is large enough to support a peak in the Krylov complexity. Sorry, the logic is slightly long, but here I show why the RAM is so important for the peak in the Krylov complexity. So in this sense, we can say the Krylov complexity, the peak of Krylov complexity is related to the spectrum rigidity. So of course, you may ask another question, but if we consider some spectrum which is uncorrelated and which do not obey any spectrum rigidity, or so what happened? Okay, here I show the result. Okay, here I consider some uncorrelated spectrum, and then we can also work out the Lanczos coefficient. In average, the behavior still looks like a Zhuo-Yu, but because I choose a very special one-point function, but up to the absence of correlation between spectrum, the two-point function is very trivial. So in this case, again, if I calculate the Krylov complexity, it undergo a linear growth, and then just saturate without any peak here. And correspondingly, if I numerically check the transition probability, you can see there's no ramp. Undergo the slope. After the slope, it directly go across to his plateau. So I think question. So yeah. So following this property, it means if we following this logic without any ramp here, it means the transition probability should be greater than his plateau value, and then you will find the Krylov complexity is bound by another quantity, and this quantity has no peak exactly. So yeah. So based on this argument, we can say, okay, if there's no chaotic in the spectrum, I mean, in other words, the spectral rigidity, then the peak in the Krylov complexity is absent. Yeah. So of course, everything above is about the random matrix example. Actually, we can also do the same game in the SYK model. For example, here's the SYK4, which is chaotic. And here's SYK2, which is integrable. And so for the SYK4, we indeed see some slope and linear ramp in the transition probability, and then we see the peak in the Krylov complexity. And as a comparison, in SYK model, actually there is indeed a ramp, but this ramp is exponentially ramp. It's a very short ramp. But we can see if we compare these two figures, the ramp here is very short, and if we consider any finite n for the transition probability, this transition probability even don't contain any ramp. So in this case, there's no ramp. So similarly, in the Krylov complexity, you don't see a peak. Yeah. So you can check this relation between transition probability, the ramp in transition probability, and the peak in Krylov complexity in another model. Okay. So now it comes to our conclusion. So so our conclusion is, okay, we studied the Krylov complexity in the random in the random metric model, and also in some SYK model, and also some non-chaotic model. So we end up with this conclusion. I mean, at early time, the linear growth of the Krylov complexity is driven by the spectral form pattern, which is approximately described by the spectral complexity. And however, this linear growth is not related to chaos. When you consider the maximal entangled state as the initial state of Krylov complexity. Okay. However, in the late time, the Krylov complexity deviate from the spectrum complexity, and we find that the transition probability is not self-averaging, but the Krylov complexity is self-averaging, and the transition probability inhibit universal rise-slope-ramp-plateau behavior, and in the chaotic case, okay, and that ramp is responsible for the peak of Krylov complexity. And of course, we may have some expectation for now for the future world. For some, as I say here, in our paper, we only consider as I say, to correctly reproduce all the behavior of Krylov complexity, we need maybe a higher point correlation, and even work out the correlator between the Krylov basics and the density and the density of energy. Of course, is there any holographic correspondence for the ramp in the transition probability? Yes, at least in the spectral form vector, there's a gravity correspondence, which is the so-called double column or trap geometry in the gravity part. Okay. And also in the Xian's paper about of Herlin and also these authors, they found in the double scaling limit of SYK model, the Krylov basic is exactly the so-called plot state they construct in the SYK model. Yeah. Can we follow this? Can we calculate similar for some RAM in those SYK model? I mean, I'm still working on this direction. Thank you. That's all.
Thank you, Zhuo-Yu. Do we have any questions? Seems not, so then let us thank our speaker again.
Thank you. Yeah. Sorry for the timing. Yeah.